Okay, ladies and gentlemen, now moving on to our session 19th of this year's NIS 2024 on AI in energy information. Can you all please join your hands together for Professor Dr. Sabita Maharjan? So, ma'am is the principal adjunct research scientist at NAMI and she's also the professor at University of Oslo, Norway. Ma'am, can you please have you on stage?
Good afternoon, everyone. My name is Sabita. I am a professor at the University of Oslo, Norway, and I also have an adjunct position at NAMI. Today I'll be talking about AI for energy informatics. University of Oslo, Norway, geographically quite remote, far up north, but I think in terms of global ranking, we are doing not bad. This is my group that is working on a couple of different things, but I like to call it Energy Informatics Research Group. I am the full-time faculty member, and we also have Professor Janzan, who holds an adjunct position, and Professor Frank Eliasson, who is Professor Emeritus. We have one postdoctoral researcher and some PhD students. And also quite a few master students and from time to time visiting researchers in the group. My research activities, as I said earlier, I like to call it energy informatics, and you will know what exactly I mean by that in a bit. But I am working on a couple of different things. These are different domains, but what exactly I'm doing is mainly resource optimization and resource management and performance optimization in smart and sustainable energy networks, including electric mobility, wireless networks, extensively focusing on vehicular networks and 5G beyond and 6G. And more recently, I am more and more interested in data privacy, data security, and the notion of trustworthy systems. Not just trustworthy AI, but trustworthy systems in general. The outline of my lecture today, the first part, I'll spend some time defining what is energy informatics. The overview. Second part, I'll talk about demand response management. And the third part, I'd like to introduce our cross-disciplinary project called PRETIM, Privacy Preserving Transactive Energy Management. Energy informatics overview. And I have two parts, energy informatics part 1 and part 2. This is energy informatics part 1. So this is quite literally what the words tell you. You have the energy system, the power grid infrastructure, which is the biggest man-made infrastructure ever, and which also is the backbone of all other networks and any other kind of system, because this is what provides you the power, without which neither the internet works, nor the wireless networks, nor the data centers, nothing else works. But then it is believed that the conventional energy system, or the energy grid as a whole, is not smart enough or is not good enough for now. So we need to use ICT, information communication, networking, and control technologies to make it smart in some sense. Therefore, energy system plus ICT is smart grid. Okay? So energy system plus ICT is this energy informatics part 1. And this is within ICT, there are a lot of different things, big data, cloud computing, edge computing, cybersecurity, and so on. But AI, or machine learning, deep learning, that's of course one part of ICT. And this is my definition of energy informatics part 1. So you will not find this definition in any book, but this is my own definition. So we want to use ICT, AI algorithms, since this is the school on AI. So we want to use AI to make the energy systems smart, or better in some sense, right? But how exactly do the AI algorithms work? What do they need? How do you train them? How do you train your AI algorithms? Do you train them on the air? Yes? Are you all hungry? 12 o'clock? No, okay. All right, I'll try to keep it short. So you see, this is the number of parameters in billions, and this is the accuracy achieved for ImageNet. As you see, you move from about 69-70% to about 80-81%, 10% improvement in accuracy. The number of parameters that you use to train the train your algorithms, deep learning networks, increases from about 500 million to about 8 billion, 9 billion. This is an alarming level of energy consumption. Do you understand this graph, right? All the deep learning, fascinating stuff, all the magic there, the magic does not come for free. There is no such thing as free lunch. All right. So the thing is, there is a paradox here, a fundamental paradox. You want to use AI to make your system smart and reliable and energy efficient and all the good things in the world. But what happens is your smart AI is, not just AI, basically everything, as I said, power grid infrastructure is the biggest and the most critical infrastructure we have ever made. So this is the story behind how the deep networks or deep neural networks work. They are massive energy hungry. So what exactly does it mean when we say, okay, so and so many terawatts, so and so many million parameters or billion parameters? Let's try to make it a bit more relatable in terms of what we usually know or what we usually do, what is more layman term, so to say. So you see, training a deep neural network, the transformers in 2019 with 200 million parameters, training them offline, that consumes about 57 kilowatt hour power, and that is equivalent to the carbon dioxide emission of 5 cars in their lifetime. You understand the scale of energy consumption, and this was in 2019. And now with ChatGPT and all the advanced versions of GPT, you can only imagine how exponentially this is growing. Okay? Yes. All right. So then I come to energy informatics part 2, which means it's not using ICT for energy systems to make it more reliable, efficient, smart, all the best things in the world, but it's also using good energy, clean energy, green energy, or making the communication networks and computation networks more energy efficient. Either more energy efficient or powering them with green energy. It could be either or both, usually both. And then there are a number of different ways to do it by using the renewable power supply to power the networks, by optimizing the power consumption, optimizing the energy, improving the energy efficiency, energy harvesting, and there are so many other techniques. Okay, but you will get the slides later on, so I'm trying to, since you guys are so hungry, you don't have any energy to, yes, so I'm trying to go a little fast, okay? All right, so now with my energy informatics definition part 1 and part 2, what I want to establish is that energy efficiency, okay, will be an overarching theme for many applications, many current, emerging, and futuristic applications. Not just for smart grid, not just for electrification of transport, not just for autonomous driving and vehicular networks, communication networks, but also for 5G beyond and 6G, the communication networks, and also for AI, all the fascinating deep learning stuff. All right. Let's take a look let's try to now zoom out a bit and see the global energy consumption at a very, very high level. So here, I don't think you can see any text from there because I myself cannot see it. So I have to come over here. Yes, sorry about that. Okay, so you see, this one here at the bottom, the top right corner, that is about the energy consumption, difference in energy consumption per year. So this is not the total energy consumption, but the increase or decrease in energy consumption every year. Okay? So from 2022 to 2023, there has been slight increase. But from 2023 onwards, or 2023, 2024, which is now, it was predicted or estimated that the energy increase, that the consumption will increase heavily. Okay, so this is the difference between 2023 and 2024 or onwards. And here you see, if you take a closer look, that all these things at the bottom here, those are emerging market and developing economies, like India. I'm not sure if I should call China developing or not, but India, Nepal, China is probably doing very well already, also India actually. So for countries like Nepal, Southeast Asia, and so on, this big chunk over here, this one, is basically the developing economy. And this one here, over here on top, that's basically the advanced economies. So what this graph is showing is that the consumption will increase heavily. I can feel that my voice, the modulation is not very good. Sorry about that. I'm probably not holding it steady, but I'll try my best. So basically, the consumption will increase heavily in the developing country or this part of the world, and in advanced economies, the total difference in total consumption will still increase, but not that much. But if you look at the individual, okay, again, I have to come back over here. So individual countries, this is for China, where you see that the consumption over here, this is about 2023, and then it had been increasing steadily. But from here onwards, it starts to fall. Why do you think that is the case? I asked a question, hello? Yes? So you see, the consumption has been increasing all the way to 2022, 2023, and then it starts falling down in China. Now this is India, and this is Southeast Asia. The consumption has been increasing, and this one is actually the projection. I know that from there it all looks the same, but this one is the projection from 2023, 2024, but it is increasing, but just slightly, not that much, or maybe quite a bit. And then Southeast Asia. And now if you look at United States and Japan and Korea, then the consumption is actually, or the demand rather, demand from the grid is rather falling down. Okay? Do you think these curves are as expected? That the total, where you see that this demand over here is more or less increasing in all countries at different proportions, but here you see in some countries the total demand from the grid is actually decreasing. Okay, I see that you don't see anything here. Okay, I'm really sorry about that. Okay, I'll tell you what that is. It's not fair to ask you questions when you don't even see the graphs carefully, clearly. Okay, so what is actually happening is the countries like India and Southeast Asia, where the consumption is still increasing at a good pace, or with a high slope, is the population is increasing, basically, okay? And you need more and more energy. The applications are exploding, of course, but mainly the population is high and it has been increasing. In China, the population is not increasing as much, or probably reducing. That's one of the reasons. And in US and Japan, Korea, and these countries, it's not that the population is not increasing at that much of a pace, but it's not that the consumption is decreasing, but it's mainly because they have massive amount of renewable energy resources, renewable power generation. That is why, because you are generating renewable power, the power that you actually draw from the grid, even though your population is increasing at A, B, or C rates, and even though your applications, computers, laptops, number of devices, everything is increasing at an exponential rate, but because of the renewable power generation, the actual amount of power that you draw from the grid, that is decreasing. Okay? So we say 2023 is sort of the correction point of time. Understand? Yes? Okay. Thank you for being so kind, for understanding it without seeing the graphs. Okay, anyway, I move on. The power grid abstract model, I think we all know power grid is something that we all have been interacting with. We all use power, right? So you have the generation, transmission, distribution networks, and the customers, that's us, either individual households or schools, this school for example, or data centers or shopping malls, all of those are the customers. Smart grid, as we learned early on, is power grid infrastructure plus ICT, right? So what do you do when you integrate ICT into the smart grid infrastructure? With this integration, you make two-way flow of electricity and information. First information and also electricity. Two-way flow of electricity possible. So what is the smart grid conceptual model? This is the NIST conceptual model, where you see the four units, the old units, the conventional units, generation, transmission, distribution, and the customers, okay? But here, you also see including DER, and DER means distributed energy resources, all right? Renewable energy resources. And why is it called distributed energy resources? Because it could be installed at different places. It could be at the generation sites, along with the GenCos, somewhere far off, offshore. It could also be with the households, the solar panels on top of our households, on top of our houses, and also solar panels at the community levels or the wind farms. So it could be at different places of this grid network. That's why it's called distributed energy resources. Okay, total accumulated distributed energy resources. But this is the conventional grid, right? More or less, if you just exclude this DER. What exactly is the new in the smart grid? The conceptual model. The new element is, there are two new elements. One is the addition of these three stakeholders: markets, operations, and service providers. Is that completely new? Did we not have any electricity market before? We had these four units, the customers, transmission, distribution, and of course the generation facilities. But how did we use electricity? We didn't pay for the electricity. Did we get it for free? How has it been working? A bit louder, please. Yes, of course, we have to pay for it, right? We don't get it for free. But the thing is, there is an electricity market and there is service provisioning and everything, but then a lot of it is static, very simplistic models. Now you have multiple service providers who all use data, your own data, and then they all try to sell you the so-called intelligence. They say, okay, you can do so and so, you can buy cheap electricity, you can do peak hour planning so and so by using your own data. But there are multiple service providers. So it's doing a lot of good. This AI, intelligence and informed decision making and everything. But there are a lot of service providers, there are operations, and there is also this market, which is more dynamic, okay, which is based on more high granular, high resolution data. And also, another important thing is these lines over here. That means the interactions between all the players, all the stakeholders. That gets more and more extensive now. Before, the customers were connected to the DSOs, DSOs to the TSOs, and then TSOs to the generation companies. That's it. It's a single line, linear relationship, linear connection. Now everything is connected to more or less everything. Okay? That means, and this connection is with the communication, different communication technologies and protocols. So this is the standard model, conceptual model of NIST for smart grid. And again, another slide where you cannot see much, but I guess. Basically what it is trying to show here is that smart grids driving energy intelligence, and it has a number of different stakeholders and functionalities. But then I'll move on. I'll not spend much time on this not so visible slide. Okay. Yes. So now coming to the topic of my lecture, AI for energy informatics or energy industry. You can use AI for a number of different things, not just for, okay, you can use AI for electricity trading and for smart power consumption or power consumption scheduling, also for virtual power plants, and also for constant monitoring and automated control. Okay, all right. So that's what happens when you just try to copy some figure from somewhere and then you don't know how the resolution will look like. And when you draw the figure yourself, this is how it looks like, okay? All right, so now I have talked too much about smart grid, I think. So three main goals, actually four, but for now let's say decarbonization, decentralization, and digitalization, the ICT part, remember? Are you awake? Wake up, people. Long way to go. It's probably some 10 minutes. Oh, no. Okay. Maybe we started a bit late, just so I get some extra minutes. All right. Okay. So see, this is smart grid. Three main goals: decarbonization, decentralization, and digitalization. And there are many fundamental components incorporating distributed renewable energy resources at different scale and in different ways: distributed energy trade, advanced metering infrastructure, demand response, and so on. The main goal, the end goal, let's say, is distribution system automation, introducing automation, automated control, constant monitoring and automated control eventually, and accurate automated control, of course, as good as possible, like Vishis was talking for healthcare, and enhanced user responsiveness and grid automation, both of them. So enhanced user responsiveness means you are not just a customer who is drawing electricity from the grid and paying every month. Not just that, but you are a more active stakeholder where you have a lot to contribute, either with generation of power or selling of power. There are different models, but more responsive users and enhanced automated control of the grid. Okay, But today, I have got an hour, so I have to choose what I want to give the lecture about, and I will be talking about demand response management. Okay? A small part of this whole thing. So here it is. Now, what exactly is demand response management? But before defining demand response management, this is the conventional curve of demand and supply. Okay, this is a response, but it should actually be supply. So, or maybe also response. Okay, so what happens is there is a demand of electricity, how much the customers need, and the supply side, generators or the operators, they try to provide you as much electricity that you need. Right? Very simple. There is a certain demand, you try to meet that demand, and it is necessary, it is required at all times that demand is equal to supply for the electricity grid. But then you might say, is it different that for any other market? You want to sell clothes, right? You sell certain clothes and some people buy certain clothes, so whatever you sell, they buy, what remains you sell tomorrow. Or maybe ice cream or some other commodity. Why is it so different here in the case of electricity? Anybody would like to speak up?
Storage problem.
Storage problem, yes. That is one. Certainly, I think you went one step ahead. So basically, when you have renewable energy resources, it's a lot of intermittency associated with the renewable energy resources. Even if it's fossil fuel-based power, you still. Yes, you try to match it based on statistical data, historical data, but it's not always exactly equal. Then you need to always have backup generation plans or storage, and it's expensive to buy electricity during those times. Okay, without going into the details, that's a whole story on its own. But here you see, there is something called peak hour. Okay, I think almost all of us, or at least most of us, are familiar with this concept that during peak hours, electricity is usually expensive, so try to schedule your appliances, use your washing machine at night, maybe charge your electric vehicle at night, and so on. So this is a very fundamental concept. But the demand response here, what happens with it is that instead of following the conventional model, where there is a certain demand, and the supply tries to meet that demand at all times. And also another thing, very important with the power grid, or with this electricity market, is that there is something called buying and selling electricity that sounds like any other commodity. But electricity is not clothes, it's not ice cream, it's not any other service. It comes through the cables where the electrons flow, where you have to keep the frequency of operation, usually 50 hertz, and that 50 hertz cannot go down to 49 or 45 or 52. It has to be 50 and 50, maybe 49.8 or 49.9 and 51.1 or 0.5, but not more or less swing than that, okay? So it's very important to keep that balance. But now it's impossible to predict or precisely predict the demand all the time. So instead of supply following demand, here what we are trying to do is the demand follows the supply. It's actually both. It's not just that. You usually estimate and you have statistical data, but the demand also tries to follow supply in the sense you try to use more electricity when there is more supply and use when there is less. And that will also reduce this peak. And of course, it will save you as a user in your electricity bill. But at the same time, more importantly, it will actually reduce those peaks, and that will contribute in improving grid reliability or grid stability. So it goes as far as that. All right. Without spending much time on this, so I'll give you a very simple example of home energy management, demand response management as home energy management, where basically, you have a number of, every hour or every time slot, you have some prices available. And these appliances, you try, instead of scheduling them like this, maybe you schedule them like this, some here and some there. So you can use the electricity when it is maybe cheaper, okay? Mathematically, mathematically comes one slide later. So in this slide, how exactly do you do that in practice? You have a smart meter. In countries like Norway, for example, most of the houses, I think 99%, between 95 and 99% of the houses have smart meters. The smart meters are connected to individual appliances, and the smart meter can switch on or off these appliances, which is basically scheduling of the appliances, as long as you have access to the price. Okay? Mathematically, this is how it looks like. Can you see these numbers? I think this is not hard to see. Okay? So XA, the demand of appliance A in our H, But then there are multiple appliances, so summation over appliances and the price in hour H, and this price is given. So you sum over all the price times the total consumption in that hour, and then sum over all the hours. And then you minimize your total cost for that day. Very simple, right? And there are some constraints, of course, that this fridge should operate between 2 p.m. and 6 p.m. and the washing machine should operate between so and so. And also some operating constraints about the power rate, how much power the fridge can draw. Okay, fridges, that's a bad example. The fridge has to be on all the time. But how much power, between what and what minimum and maximum power the washing machine can draw, and so on. So these are some constraints, but you have to solve this problem, which means this is your optimization variable. This is a very simple problem. As long as you know pH, the power price, unit price of power in that hour. Now, how does the same problem look like? Is there only one household in this area? Did you hear my question? Sorry for being, but I think sometimes you need to do that, when it's close to lunchtime. This was a bad time slot, Bishes. No, okay. Yes, see, so of course it's not one household, right? When it comes to neighborhoods, energy neighborhoods, these are smart energy neighborhoods where you can actually do peer-to-peer energy trading among the households. But I mean, even otherwise, in general, how do you formulate the cost minimization problem for a smart energy neighborhood? So I actually plan to do this on the whiteboard or blackboard, but I realize I cannot do that. So I'm going back over here very quickly. See, what will be different in this formulation if we want to do it for a smart energy neighborhood, or a neighborhood basically? What would be different in this case? Somebody? Yes, would somebody like to volunteer? No?
As it is mentioned, ICT is smart. I think we have to integrate the internet things.
Okay.
I'm not sure.
Okay, but thank you very much for speaking up. A big round of applause for the speaker. Let's do that. All right, see, to keep things simple and also to respect the timeline, what we basically do is, this is the summation over appliances for one household. We add another term here, okay, which is the summation over individual households. But the final summation comes over here about the hour. So it's all the appliances of one household, all the households, and then that particular hour. And then next hour the same. So 24 hours usually. Could be half an hour, 15 minutes, but typically 24 hours. Okay, so that would be the case. And that problem can also be solved easily, with not that much difficulty, although the scalability will be an issue. But then as long as P is given, it's not a big deal to solve that problem. In practice, in reality, do you think P is always known? The price in that hour of time. Okay, to make things simple, it's not. The energy price is a variable. It has different models, of course, but it's a stochastic variable usually. That also depends on the load. So it's not load times electricity price, but it's load times price, which is also a function of load, and not of one household, but multiple households. But also each household's consumption depends on the consumption of other households. So it's a very complicated dynamics. So I'll give you an example. If it is only about peak hour, even if the pH is given, if I say, okay, I should charge my electric vehicle at night, because usually the electricity is cheaper at night. All my neighbors do the same. So what actually happens, the peak hour shifts from daytime to nighttime. And the same, it keeps shifting, right? So the my optimal strategies depend also on that of others, and so on. And the price is also a variable. So in reality, it's much more complicated, So then in this paper, what we do is, this is the paper of one of my PhD students who has graduated, who finished his PhD in 2022. But I always like to brag about this paper because it's published in TII, Transactions on Industrial Informatics, 2021. Yes, so in this case, we jointly model the interactions between the households as a non-cooperative stochastic game while using deep reinforcement learning to implement the distributed learning. So this is the model here. We have a number of households. Each household has a controller, ECC, and there is an aggregator that talks or communicates further with the DSO. I'm really sorry about this. I feel, no, I'm genuinely sorry for this because I could see while I sat there, somewhere in the middle, that I couldn't see much of the text. But okay, so basically here what we are doing is we are calculating something called lambda, which is the generation cost. So the price that you actually pay is not always equal to generation cost, but it's usually indicative of the generation cost. And the generation cost is usually quadratic. Okay? And then the total load in the grid is the non-shiftable load plus shiftable load scheduled. That is the total load. And the real-time pricing is related to lambda based on the load threshold, which means as long as the load is within certain threshold, then it's basically the generation cost. But as load increases, then you also scale up the generation cost. Okay? And again, sorry about the text size, but you all will get the slides, and you can always contact me if you have questions. Yes?
Yeah, so generation cost is quadratic in what? Quadratic?
Generation cost is quadratic in the amount of power that you have to generate, or which is basically the load. Yes. All right? Oh. Okay. Very good. Okay, you know what? So this is the electricity cost, and which we eventually formulate as some form of reward for the deep reinforcement learning, DDPG, and the expected accumulative reward. Sorry again. But the thing is, as I pointed, you don't have to, well anyway, maybe I'm not that sorry, because you don't have to understand each and every variable here. Anyway, okay, so yeah, I take back a bit, maybe 50% sorry. But anyway, so the thing is, you see, JI here, that is your expected accumulative reward, and I'm sure that you've had lectures on reinforcement learning before, so I take the liberty to understand that you understand that part. So you see, the expected accumulative reward, but all the households are not cooperative. They are only interested in maximizing their own benefits or minimizing their own costs. They don't care about other households, okay? So this is basically a Nash, the non-cooperative game setup, where you optimize your strategy or your best response given the strategies or given the consumption scheduling vector of other households. This is the Nash equilibrium best response expression. Yeah. And then this is your optimization problem for each ECC, the energy consumption scheduler or controller. And in this case, one of the main differences, the main innovative idea in this paper is that we have a so centralized critic and distributed action. Why? What that does is that, you see, this is the centralized one, which means the aggregator solves everything. It just collects some data from the households and then solves everything. This is the completely distributed one, which means the consumers or the households solve it independently without talking or without sharing their individual data with each other. But then we have the centralized control and critique and distributed action. So initially it starts somewhere here, but eventually it catches up. The performance in terms of the reward is same, more or less, as that of the centralized structure, the centralized algorithm. Okay, so that's that. I'll stop bragging about this paper over here, but I will try to give you a bit broader, broader view, okay? So these are simpler ones, so I'll take them quickly. So we learned that there is home energy management, smart home energy management. It's a demand response problem, and we saw some complicated reinforcement learning based approach. But is that DRM? Is that it? That's a very simple, I mean, we are talking about households and the neighborhood, but it's not, interestingly, okay? So the DRM examples, broader view. Now this is a household. It's not only about scheduling your appliances in time, but it can also be about choosing different providers. You want to buy electricity from provider A, B, C in real time. Every hour you can switch, for example, okay? Or it could also be prosumers. When you say prosumers, you see the word consumer and prosumer. Prosumer means the one that does not only consume, but also produces its own electricity and also consumes. So it could be prosumers, which means they also have their own solar panels or maybe some other form of renewable power generation. Okay? And then, in this case, the dynamics becomes more complicated, but I don't want to bore you more with that, and also I have limited time. But in this case, it's both multiple providers and multiple prosumers. And the interactions actually become very, very interesting. So what? That's that. Now, the data centers, Google data centers. You must have heard, I understand that most of you, some of you are PhD students, some of you are master students, but many of you are undergrad students. So you must have heard, computer science students must have heard that Google data centers are somewhere placed in undersea, somewhere in Norway, Finland, all the cold countries. Not all of them, but some of them. Have you heard about this? Yes. Why do you think that is the case? Yes. Data centers are one of the huge energy consumers, and increasingly so with all these fascinating deep learning algorithms, because you need to perform a lot of computation, storage of course, okay? So they are one of the biggest consumers of electricity, and then you try to minimize the energy consumption, the cooling part, energy consumption for cooling, in addition to doing the actual task, of course. Okay, and then in reality, of course, they are not only placed, this is Norway here. So Norway has a very good market actually for data centers. It's a booming region, obviously because of the cold weather, which I don't like very much, but apparently for data centers, it's a really good business venue. But anyway, not all the data, these are Google data centers, for example. This might be a bit outdated, but more or less representative. So they are also in Singapore, also in the US, also everywhere, basically all over the world. But then, if Norway is so cold, Finland is colder, why not put all the data centers in Norway or Finland or Denmark, huh? A bit louder, please. Say energy, something must be right? Yes, okay, very quickly. So the thing is, of course, the cooling, energy for cooling is one key factor, but also there are other factors. The main load, the client request, right? You need to access certain data, perform computations. They don't only come from Norway and Finland. Maybe there is naturally less requests from here. You have requests from mostly maybe US, maybe other parts of the world. You also have to satisfy other QoS constraints, usually latency, other constraints. So of course, not everything in Finland and Norway, okay? And another example of DRM is the cross-border electricity trade, where Norway actually sells. By the way, maybe how many of you know that Norway actually has almost close to 100% renewable energy, hydropower? Did you know that? Yes, and actually Norway has many collaboration projects with Nepal, where they work together in also KU, also mostly KU, but I think also others. So this cross-border trade, where Norway sells electricity to other parts of Europe in summer, and in winter, it's very cold in Norway, so we have to buy the same electricity at a much higher price. Not very smart, but this is also an example of DRM. Okay? So all examples don't need to be smart examples. They can also be real examples. All right? Okay, now, very quickly. So this is probably the last slide on DRM, and then I'll quickly move over to the project. But this is a very important slide, so please pay attention. So we talk about the DRM, we talk about the prosumers, the end users, and minimizing energy cost or improving energy efficiency. But what are the implications of this peak load and demand response management in terms of capacity planning and investment and from the investment perspective? So what happens here is usually the grid should operate the highest peak possible. This is from 2011 to 2014. Highest peak possible, 20 to 25% over that highest peak possible. So the capacity of the grid should be about this one. Okay? So that's about, I don't know how much, 10 terawatt hour, and then it should be 12.5. Now imagine if you're able to cut off some of those peaks, the highest peaks with demand response management, data centers, households, everything, using low-cost AI instead of, transformers and ChatGPT, but yeah, that's just hypothetical now. But anyway, if you're able to cut some of these, oh, very good. Okay, yes. See, then what happens is this line comes down here. So if your peak were about 10 terawatt hour, and you are able to bring it down to 9, then your capacity comes down from 12.5 to about 10, or 10.2 terawatt hour. Okay, so what does that mean in terms of capacity planning is that you can have a grid infrastructure that operates that at a maximum of 10 terawatt hour instead of 12.5. So it's only 2.5 terawatt hour difference. But in terms of capacity, that's a lot. And also in terms of investment, this basically means you are saving millions of dollars, billions of kroners, either saving or you are postponing the investment by 10 more years. You understand? Okay, so that is the implication in terms of this simple DRM. The concept is very simple, but the implications are profound and deep to the infrastructure. Okay, now I know that I don't have much time, so I will try to go through this project very, very quickly. Pre-term project, privacy preserving transactive energy management. The project is called Privacy Preserving Transactive Energy Management. This is also about an advanced or more distributed, decentralized form of energy systems, where we do study about privacy, about the whole, we take a holistic approach, but we do focus on privacy. Why? Because there are actually a lot of pilots. For example, the Brooklyn microgrid in New York, or Empower the Valor microgrid in Norway. Many other initiatives here. These are all the Norwegian, the national projects. On distributed energy systems. This is Colombia, Bangladesh. This is a service provider in Australia for distributed energy systems. So actually, technologically, the area is quite mature. And the energy systems, well, of course, you need money, but the energy systems, research and system optimization research is quite mature. But still, you will only see pilots, like the Brooklyn microgrid and the Valor microgrid and others. But you will not see the real commercial deployment where stakeholders, the prosumers are really active and they exchange signals and they participate and so. That's still not a reality, while the technological readiness level is really, really high. So what happens here is that we think that this part is really mature, the technological part. But we believe, our hypothesis for this project is that the psychological, socio-psychological factors of the prosumers, of the users, and also the regulatory and policy aspects in terms of data, collection of data, in order to make them more, in order to facilitate this participatory approach, this is what is lagging behind and we need to catch up, okay? And privacy lies at the intersection of all of these. So this project is about delivering a holistic framework to generate new knowledge through cross-disciplinary research, novel research and high impact results for the blah, 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 sustainable energy system. Project team, we have two professors from I'm leading this project, coordinating this project, from IFI, the Department of Informatics, but from psychology we have two professors. From IFI we have many professors, but many of them are actually adjunct or emeritus, except Roman, who is a full-time. And I am leading. We have two professors from the Faculty of Law, but from different departments. Catherine, she is a professor of energy law, okay? Energy law in Europe, in Norway and in Europe. And Lee is a professor of data law and data legislation in UIO, of course, and within the same faculty, but from different departments. And we have two professors from the Department of Technology Systems, which is mainly energy systems. And I and my team is from energy informatics. And we have two postdoctoral researchers and 5 PhD students working in this project. And these are the industrial partners. Nordpool is the European energy market operator, and NVE is the national regulator for water, energy, and waste. So this is the project team. I think I am going to skip some of these slides because I would like to use some time for discussions. Okay, so we do a lot of work on the energy edge, which means mainly on the prosumers. While the infrastructure, of course, you might need to scale up at some point, we do really believe that all the dynamics, the rapidly changing dynamics and complexity lies with the edge. Edge means the users and all the resources close to the users. Okay, I think I will skip a lot of it. And then we try to empower the prosumers in this project where we try to address privacy concerns, secure data sharing, design secure data sharing models, and also define the notion of trust of users in the system. Before I recall that Bishesh also talked about trustworthy AI. This is not only about trustworthy AI, but trust in the system. It's two different things, not completely unrelated, but two different things. But how do users trust in your distributed or transactive energy system, for example? And that notion is very subjective, but we try to define the notion of digital trust and so on. Okay, this is the project work package structure. I'm lagging a bit behind time, but as you see, we try to optimize the energy, the edge landscape, and in terms of both energy efficiency and towards a resilient grid, because the edge does not operate alone. It operates with the grid, of course. Everything is connected. This is a very recent paper of ours, one of my students who just finished her first year, the first author here, and this is a preliminary paper from Smart Grid.com, which we held in Oslo in September this year. And here we talk about customized privacy. So empowering users by providing them their preferred level of privacy. So how much data, how much noise do you want to add when you share your model parameters? That's basically the idea in simplest terms. Privacy preserving, personalized pricing scheme. Personalized in the sense your privacy coefficient is personalized. And this is the system model where the users, they establish a contract with the aggregator, which means you can choose not to share your data or share your data with certain level of noise, which can vary. And then based on how open you are to sharing your data, you get your discounts later on from the DSO in your energy pricing, energy cost. Okay? Some results here, some preliminary results where we actually see that even with different privacy levels or privacy coefficients, your energy cost minimization problem still can converge. But of course, even for the similar setup of appliances, you might get different energy pricing discounts. So this is with the more dynamic setup of the privacy coefficients. But I think I will keep it over here. I'm going to skip this one. But I would like to end my lecture with, okay, not bad. So I would like to end my lecture with this Outlook slide, where for AI for energy informatics, I did talk about quite a few things, but I think I couldn't talk, there are a lot of things that I couldn't talk about in this 1 hour. Of course, you are welcome to reach out to me. But I think in the next 5-10 years, maybe 15 years, this is where the research in this area is going. Some of them are generic, where AI for system A, system B, healthcare, AI for networks and so on. It might be generally applicable, but in some of them are applicable specifically to energy systems or transactive energy systems or more distributed forms of energy systems. So the conventional ones, energy efficiency and power grid reliability, power flow reliability, those are conventional metrics, and that scalability, latency, these will remain relevant, of course. They are always important. They should always be there. Without those performance metrics, it's incomplete, basically. But more and more, technologically, we need more and more low-cost edge solutions. What that means is that if you want the users, customers or prosumers, to be a part of your grid, to be more participatory, to be an active stakeholder, in that case, you need to equip them with the computation capability. The smart meters, they can send you some data at 1 hour, at half an hour, every 15 minutes, but they usually don't have a high computation resources available. So you need to design it, From 2013 onwards, it was more about data, more data, big data, better performance, more accuracy, and so on. Now we can clearly see the shift where you don't need big data, okay? Maybe you need 10 times more data to improve the performance by 1%, but who cares? Especially it might be different again, I do not generalize it, but for operators especially, they care about revenue and business, and they don't want to spend so much to, if the accuracy is about 80% and they need to train it, it's 10 times faster, obviously the operators will go for that one. But anyway, we need to equip the edge. Edge means the prosumers and the nearmost servers or resources, aggregators, for example, but low-cost solutions, those that are effective with small data. On the other hand, data privacy is increasingly important. Distributed processing, explainability, interoperability, and the notion of digital trust and transparency are extremely important, and they will only become increasingly extremely important. Okay, anyway. And then in this context, when you look at both of these, secure data sharing, data ownership, data law, and also energy law or energy legislation, I believe will be increasingly important as well. All right, some references, and I would like to now open the floor for questions. Thank you.
Namaste. My name is Vivek Pathak. So you were talking about a paper that you presented about mass equilibrium, about the energy consumption, right?
Mm-hmm.
So my question was, I think from what I know, the strategy that you develop would be like an optimum energy consumption strategy for the whole network, right? So would there be other strategies that each individual household would like to perform so that they would be optimizing their own gain and might deviate from the optimum strategy?
Yes, in this case, actually, the households are performing their own optimization. So it's not for the whole network. Ideally, the Pareto optimal solution for the whole network would have been desirable in terms of the utility and the value. But of course, this is the whole thing. The households are performing their own optimization. That is why you have, I'm really sorry, it doesn't help much, but here, you see, you have this JI over here, which means it's the ith household. Okay, the expected accumulative reward of the ith household, and it chooses it, or it optimizes its own utility or its own reward. This pi asterisk theta I is its own best response given pi theta minus I. Okay, the minus I is basically all other households. So the households are performing their own optimization individually, but with the little bit of help in implementing the critique here at the aggregator level. This is the aggregator that has a critique function, critique network, and these are individual households. So you see the action function is here in the households. The critique is at the aggregator. So this is the whole trick in the paper, that you perform it in a distributed, so we call it centralized critique, distributed action. So your actions are still computed in a distributed manner, iteratively, but you have some help from the aggregator in terms of implementing the estimating the key function.
So the aggregator is just providing the information about other households to...
No, it doesn't. So that is the whole thing. The households are not interested, they don't want to share their data with other households, okay? But the aggregator has a trusted third party. The households can share some of their data, not their appliance consumption, everything, but some of their data, their feedback with the aggregator, and based on that, the aggregator does not share any data of household number 1 with household number 2, but it just gives a feedback on it just provides a critique to the, okay. The critique provides the critique to the actor network, so it can improve over time. But I think I know that it's not that easy. You cannot see anything there, and it's a bit, it's not that easy, but I suggest that I can send you the paper, or you can download the paper, and we have more details there. Okay?
Okay.
Yes, thank you.
Thank you for nice presentation. My name is Paul Kumar Bide. Is nuclear energy is part of NIST smart grid conceptual model? If yes, how? If not, why not?
It's a very good question, actually, but I'm not sure if it is right to ask whether it's there or not. That's, of course, the right question. It's okay to ask that, but why it is not there, or any specific definition or conceptual model of nuclear energy, that is probably not the right question to ask. But yes, it's a part of renewable energy. It's cleaner than many other forms of energy, certainly. But in the NIST model, it doesn't specify as anything specific or in detail, which is very different for nuclear energy than for other forms of energy. So that's not the case. Why? Well, I think I cannot speak on their behalf, but of course, I can give a representative answer. When you say DER, distributed energy resources, so you can interpret it like it's a part of this DER, okay? Because this is renewable energy resource. So it's not explicit and direct, but I think it depends on your interpretation. Why it is not there explicitly, I don't know. But I would like to believe that it's a part of this renewable energy resources. Yes.
You mentioned that before with the Korean Electric Power Corporation. So when I was there, I had like a lot of internal views of the demand of the more energy with the electricity car charging center. But I've seen Norway, like Norway has success of the distributed electric car and electric charging center. So could you like brag yourself of the Norway, how was successful like distributing like electric car and electric like charging center? Because it's like smart home expert.
Thank you for asking that question. I'm glad to talk about Norway in general, the place where I live, and also about electric mobility in particular, although I excluded many slides. I had some on electric mobility as well. Many of you probably know, but for some of you it might be a new information. As what's your name?
Jane Cho.
Okay, Jeng Cho, as he pointed out, Norway is one, it's called the EV capital, the electric vehicle capital of the world. The reason being that the number of electric vehicles is highest per capita in the world, in Norway. And we've actually been very successful. It has both positive and negative implications. This came with a lot of benefits to promote the use of electric vehicles, to promote to cut off on fossil fuels. And now almost every household has at least one electric vehicle. There might be some exceptions, some have two or multiple electric vehicles, but at least one electric vehicles, we have one as well. So we've been very successful, I think, on electric vehicles. But that does not necessarily mean it's a good thing. And I'll also tell you why. Because 5 years back or 8 years back, there were a lot of those schemes where you receive subsidies, not on the total price, but usually on parking fee and small things, tolls and this and that. You don't need to pay parking fee if you have an EV. You don't need to pay for entering the central region and so on. I actually had a very nice, one of my master students a couple of years back, he did a very nice thesis on charging optimization and the deployment of charging stations and the capacity of charging stations in central downtown Oslo. I want to show you that, but yeah, maybe you can help me a bit. Yeah, so we have been very successful, but the flip side is that initially there were a lot of benefits for EV buyers, but over time, over a period of 6 years, 8 years, it has all been, thank you. Yes, it has all been taken away, unfortunately. Yes, so, yes, now I think it's coming to the second phase where now government knows that everybody has bought an electric vehicle. So now they started saying, no, you also need to pay a parking fee, even though you own an electric vehicle. Now you also need to pay toll. It's half the price compared to benzene vehicles, but you still need to pay. Now they are saying, no, you need to pay as much. So basically there is a flip side as well. Now most of the households have an electric vehicle, maybe two, and one non-electric vehicle, but it's also costing us, it's not turning out that good. Okay, anyway, but that's that part, the non-technical part. On the technical part, this is the master thesis work of one of my master students, of course, where he designed the charging capacity. So how many charging stations do we need in the city center? This is downtown Oslo, okay? This was not included in the presentation, by the way. Those of you who are wondering, oh, did I miss that? So you didn't. It was just a hidden slide. So yes, and he did plan with the real data. This was in 2017. He graduated 18, I think. But there was this thing back then that from 2020 onwards, no benzene vehicles will be allowed in downtown. And we are trying to implement, the government is trying to implement that very aggressively, so to say, but that has not been the case up to now. There are still some non-electric vehicles that go through downtown, but of course they pay much more toll and heavy prices. Parking is anyway difficult. But in this case, we did charging station capacity planning problem. One of my master students, yes. So overall good, but there are also flip sides. And the research on this part is on electric mobility is very strong actually in Norway. Yes? Okay. Thank you. Hello, my name is Sabita. I am a professor at the Department of Informatics, University of Oslo, Norway. My research activities are in the domain of a couple of different things, energy informatics and wireless networks, and more recently privacy and data security aspects as well. I have been associated with NAMI for quite a few years now, from 2018. We organized the first NAMI Winter School, AI School in 2018 December. It was quite an experience for us as the organizing team from NAMI, but I think also for the students, the first of its kind. It was a very good event, of course. I think there were the first edition were about 100 or 150 students, I think. I may not remember the exact number, but something like that. And I was blown away by the students, the overwhelming response from the students, the kind of exposure that they got, the networking opportunities, to name a few. Basically, it was just mind-blowing, really. So it started from there. I was involved in both organization, and I also gave a lecture in the first winter school in 2018. Then over the years, I think this is the 5th edition of the AI school. And I have been involved in different roles in some of the winter schools as both in the organizing committee, and also I also gave the lecture in 2021 edition, for example, and this year. And it has been a great experience. It's just so good to see opportunities opening up for the students of different levels. I remember, I may sound like an ancient creature, but I remember my time when I was doing a bachelor degree, and how limited our exposure was, how we basically didn't have any exposure at all. So I think this is great, and students have given wonderful feedback. Students not just from Nepal, but from all over the world. So I think it's great, it's amazing. But in addition to the organization and the students, I think NAMI's own journey from the first edition up to now has also been something to learn from. I can literally see how we were all doing everything by ourselves in the organization. I did certain part of it, but other the founding members who were involved much more, and it has been quite a journey also for NAMI. And now this year especially, I see a lot of responsibilities being delegated to the responsible persons in charge, and I see the organization has been very professional, well organized, well structured. So yeah, I'm glad to see the progress, and good luck for the coming years.